We get the magnitude of the torque by applying this simple formula that you see here. The Greek letter tau, which means torque, is going to be equal to the force times the lever arm. The lever arm is going to be the distance from which you are applying the force. For example, in here, the lever arm is going to be this distance, okay? From the point that you want to rotate and to the point where you are applying the rotational force. That is going to be the lever arm.
Torque is a...
Okay, now take a look. We're gonna be measuring torque in Newton times meter. The reason is because force, is measured in Newton. And the lever arm, we're talking about a distance, okay? We're talking about a distance, and distance are measured in meters. So the SI unit for torque is going to be Newton meter. So that formula is very simple to apply, but sometimes you're going to have many forces acting, so you have to apply the formula many times. Just like we do more or less with vectors. You can get the component of a vector, very simple, okay? But when you need to get the result of all the vectors, you have to add them all and to do the procedure in the table. So as you notice, the more forces you apply, you're going to be doing more procedure. But in this case, we're going to focus just on the main formula. A force multiplied by the distance. This force is applied from the pivot, or in this case, the rotational point. Now, as I told you earlier, torque is about rotational motion. Okay, so what's going to happen? In this section, we will isolate rotational motion. In particular, we will explore how to measure the ability of a force to rotate an object. Another example of torque is, for example, when you want to drink a soda, okay? So you need to twist your wrist, okay, to open a bottle. That is another example of torque. You do that every day. Remember the video I sent you about what is physics? We are surrounded by physics, but we are just not aware of that yet. In this section, we will examine a related type of motion, the motion of a rotating rigid object. Now, the magnitude of a torque. Remember what magnitude is. When we talk about magnitude, we are talking about a number, okay? How big or short something is. For example, 55 miles per hour versus 60 miles per hour. Which velocity has more magnitude? Between those two, which one has more magnitude? You can write it in the chat if you are too shy to speak.
60 miles per hour.
60 miles per hour, that is correct. So between 200 and 120, which one has more magnitude? Exactly.
200.
Between 200 and 3,785.
3,785.
Okay, that's 3,000 whatever, okay? So you see, when we talk about magnitude, we talk about a number. We refer about a number, okay? Now, I can have two numbers. I can tell you which one is bigger. Wait. I can tell you which one is bigger if 1 kilometer Okay, I can ask you, what has more magnitude? 1 kilometer or 0.6 miles?
It's the
I think
same.
they are the same.
They're the same? Well, yeah, I chose probably the wrong number. 0.6 times 1.609. Yeah, rounded is going to be the same. Yes, in that case, they are the same. They have this almost the same magnitude. Okay, so in this case, guys, yes, the kilometer is going to be a little bit gonna have more magnitude than the mile in this case. But you see that point. To compare things, we need the two things are in the same units, so you can do a proper comparison. So how are we going to measure the magnitude of a torque? Take a look to this hinge rotation in the figure 4.2. It says, of course, I included a figure because it has a cat, but it also has a point, okay? The cat flap door rotates on a hinge, allowing pets to enter and leave a house at its will. So what happens when the cat goes out? So this cat applies a force, okay? This force that this cat is, the pushing force is going to open this door. So this door is going to be able to make a rotation. So this kind of rotation is the object of study of torque. Guys, do you hear that noise?
Yeah.
Yes.
That's my neighbor. He has a workshop. Well, I will try to continue. Sorry about it so much. So the door is free to rotate around a line. This line is this one, okay? Where the hinges are. That is a rotation that occurs around a line, okay? So the ability of a force to rotate an object around some axis. No puedo. Wait. Okay, so by definition, torque is going to be the ability that a force has to make an object rotate. Okay, that's the simplest definition that we can find. Now, this axis where the rotation occurs is going to be known as axis of rotation. Some other times I'm going to call it hinge. Some other times I'm going to call it pivot. But in the end, they are the same thing, okay? So torque is going to depend on the force, but also from the lever arm. You saw that in the video, okay? In the video, a force of 90
Torque
Newton
is a
was
measurement of
applied,
90 newtons, which
okay? The force in this first, with the first range of 30 centimeters, the force applied was 90 Newton. In the second one,
if we applied the same
the force is exactly the same, 90 Newtons. But in the end, when did we get more torque? In the second example, in the longer range, because in that case, the lever arm help us to get more torque. So in that case, when you have more torque, that means that things are easier to rotate, okay? That is more torque. So the idea is that we can get more rotation by applying less force. To do that, we need to increase the length where we can apply the force, okay? So in this case was possible because this guy had two ranges, okay? One of 30 and one of 60 centimeters. But some other times you cannot change the distance where you can apply the force. So what do you have to do? Only to increase the force. So the torque is going to depend on that force, but also on the lever arm. How easily an object rotates is going to depend not only on the force, but also where you apply the force, okay? Where you apply the force, the farther the force is from the axis of rotation, it's going to be easier to rotate the object. So more torque is going to be produced. The perpendicular distance from the axis of rotation to a line drawn along the direction of the force is called the lever arm. A good example of torque that we do every day is when you open a door, okay? Now, there is a point that is never going to rotate, but this point is going to allow rotation to occur. That point is known as axis of rotation, also known as the pivot point, okay? So take a look in here. We have a door. You don't see that because you just see a line and a point in the end, but that's a door. It is an upper view, okay? So a force applied to an object can produce a torque. This torque in turn causes the object to rotate. Now take a look. This force is being applied in here. So the rotation that is going to cause is this one. Now, this distance is important. Remember, it's a lever arm. If I apply a force closer to the hinge of the door, it's going to be a lot more difficult to open it because of the lever arm. This lever arm that I'm drawing in this point is a lot less than the one I had. That's why the doorknobs are located here, okay? Not closer to the hinge because of torque. So we're going to have two kinds of torque to apply. Simple torque, which is the one that I'm going to show you in this moment, and torque at an angle that I'm going to explain next week, okay? In this case, the simple torque, you can see the lever arm from in this case, the nut and where the force has been applied. And the torque or rotation, as you can see, has this direction. But this one is more for angular torque that I'm not going to talk about yet. So let's focus on the easy one. Now the signs of the torque. Torque can have two signs, positive and negative. If the rotation produced by the torque is counterclockwise, that means that it goes against the clock, it's going to be positive. But if it goes with the clock, okay, in the same direction as the clock, then it's gonna be known as a negative sign of torque because it goes clockwise. Now, we will use the convention that the sign of torque resulting from a force is positive if the rotation is counterclockwise and negative if it's clockwise. Now, let me share with you this the whiteboard. It says, calculate the torque applied on a pencil when a force of 10 Newton upward is acting on the tip of the pencil, as seen on the figure below. The pencil is 18 centimeters long. Okay? So remember what we need to focus on. We need to focus on the formula of torque. So we have the sketch, we have the figure, that tell us precisely what is acting on it, okay? So let's see. Guys, remember that we started the class at 7:10, so the class must end at 7:50, not at 7:40. So I'm going, when the meeting is over, please click again on the link. Next time, I better send the link at 7:10. Yeah, that's going to be better. Okay, so this is what we have, okay? We have the sketch, we have the pencil, and we know that the force applied is 10 Newton upward. Now, what else do we need to know? We need to know where the pivot is, okay? So consider that the pencil is being held from the eraser part. This is going to be the pivot or the axis of rotation point or the hinge, okay? So we applied the formula for torque, which is the Greek letter tau, force times lever arm times sine of the angle. Question, what angle I have over here?
90.
A right angle?
Exactly, 90. And what is the sine of 90 degrees?
One.
1. So what happens when you multiply times 1? It's going to give you the exact same. So take a look. Whenever we have a force with no angle applied to an object and it says calculate the torque, you can totally forget about this part of the formula because we're not considering a real angle. The reason is perpendicular forces are going to give you always 90 degrees because that's actually the definition of perpendicular. So whenever a force is applied perpendicular, what you can tell is that you're not going to use the entire formula, just force times the lever arm. Another thing is, imagine that I want to know okay, imagine that I'm going, this is my force 1 and this is my force 2, okay? If I apply the force 1, am I going to be able to make a rotation of the object? Does rotation occur?
Yes,
Yes. If I apply a force 2 on this object, am I going to be able to rotate the object?
no,
No. Okay. So always try to see that, for example, because sometimes you're going to have forces that are going to act in 2 dimensions. So always you have to use only the force that causes the rotation. Okay. Always try to use just the force that is causing the rotation. In this case, this one is never going to rotate the pencil. Now, to get this torque is pretty simple. Remember, forces need to be in Newton, and the lever arm, which is a distance, must be in meters. Do I need to perform a conversion before the application of the formula? Do I need to do a
Where is the meter?
from centimeters to meters? Okay, so you do the conversion of this one, giving you 0.18 meters. How? Well, dividing by 100, you know. Okay, now that I'm going to solve the problem, I'm going to end the meeting, and please join the link again for the remaining 7 minutes. Join the link, the same link.